I am Javier Arancibia and I work on the lithium rotation connection in pre-main sequence, solar and low mass stars, where for a given temperature, fast rotators tend to be lithium richer than their slower rotator siblings. This relation can give us insight on the transport process in the interiors of the stars, but we need to investigate its universality, evolution, and environment dependence. To test the environmental effects, we checked the case of the stellar stream Piscis Eridanus, which is similar in age to the Pleiades. We found that the lithium rotation relation was comparable with the one in the Pleiades, which means that this relation might be independent of the formation scenario. To test the evolution, we studied two cases. One was TW Hydra moving group with an age of 8 million years. Although we have a small sample, we found a hint that the lithium rotation connection is already present at these early stages. In the case of Upper Scorpius, at an age of 8 to 12 million years, the scenario is a little bit more complex. Although the lithium rotation relation is not clearly seen, as in the other association, we do found that the lithium-rich objects were in general fast rotators. This behavior is confirmed by examining the cumulative distribution function of rotational periods for the lithium-rich and lithium-poor subsample. If you're interested in my project, please visit my poster. Thanks.
My name is Luisa Rabol, and this plot really is the heart of my poster. It is stellar rotation period against V minus K color as a proxy for mass. Each one of these boxes is a different cluster at a different age, and they're organized in age from low to high. In each cluster, the black points are the rotation periods for stars in that cluster. An additional red circle means there's an infrared excess or a circumstellar disk. For each step underneath, there is a gray collection of points that corresponds to a later cluster in the sequence to guide the eye so that you can see what kind of structures are appearing or changing between these cluster ages. The newest addition is Upper Centaurus Lupus, Lower Centaurus Crux, which is here. Most of these clusters are with K2. This is with TESS. Most of these clusters have several hundred stars. Upper SCO has 800. UCL and LCC have about 4,500 stars in this plot. You can see that the M star sequence is similar to what's in Upper SCO, or for that matter, the Pleiades. The higher mass hook is not well defined in Upper SCO or UCL LCC. It's very well defined by the Pleiades. There is a pileup of disked stars at 2 days in both Upper SCO and UCL LCC. This is almost certainly a signature of disk locking.
Hello everyone, my name is Natália Landim. I'm from Federal University of Viçosa, Brazil. I will talk about the impact of disk locking on convective turnover times of low-mass pre-main sequence and main sequence stars. By using the Atom evolutionary code, we determined convective turnover times for rotating models conserving angular momentum and models considering the disk locking mechanism during the first 3 million years. Disk locking models produce convective turnover times smaller than those obtained with models conserving angular momentum. We used our theoretical convective turnover times to calculate the Rossby number of 73 stars in the sample of Vidotto and collaborators 2014. We fit the data with a two-part power law function, and the best fitting slope for the unsaturated part of the rotation activity relationship was minus 1.76, and the saturation level of the fractional X-ray luminosity was minus 3.27. The differences we found between disk locking models and models conserving angular momentum suggest that properties of the disk phase of the star affect its Rossby number and its position in the rotation activity diagram. Finally, our fit to the data is consistent to those usually found in the literature. Thank you for your attention.
Hi everyone, my name is Julia Roquette and I work at the University of Exeter as part of the ERC project Awesome Stars. In my research, I investigate how the environment of star-forming regions influences the rotational history of low-mass stars. For that, I model the spin evolution of stars while using the results of viscous disk dissipation models with FUV external photoevaporation to constrain the disk locking duration. In regions of high FUV radiation, such as the neighborhood of massive stars, reduced disk lifetimes result in shorter star-disk interaction phases. Hence, stars evolving under high FUV radiation start the pre-main sequence spin-up phase earlier and reach the zero-age main sequence rotating faster than stars evolving under low FUV radiation. When combined with spin evolution models, disk dissipation by external photoevaporation can explain the stellar mass dependency seen in the period mass distributions of observed young clusters. By modeling the spin evolution of populations of stars in entire clusters, I've also been studying how clusters' properties like density and massive star population can radically influence the spin evolution of members, resulting in environmental fingerprints that remain visible in the period mass distributions way past the zero-age main sequence. My takeaway message is that we should care more about the star formation environment. And if you want to know more about this research, take a look on my poster and at our recently published paper.
Hello, my name is Robin Mantel and I'm a PhD student at UCD where I'm working with Rebecca Garcia Lopez. Here I will give a short overview of our spectroscopic survey of a large population of Herbig AEB stars and our first results concerning the star HD 141569. This high-resolution survey was conducted with the HARPS North and the Diano spectrographs at the DNG, which observed 25 stars in the optical and near-infrared simultaneously. HD 141569 is a 2 solar mass field star of spectral type A0 and is believed to host a hybrid disk. Its spectrum shows prominent double peaks in the forbidden oxygen lines in the optical, as well as in all hydrogen recombination lines covered. This suggests an origin from gas in Keplerian motion around the star in the inner disk at varying radii. On the right you can see the line profiles on the Passion series and their fits. The peak velocities in the forbidden oxygen line suggests an origin from orbiting gas at a radius of around 1 AU, which is consistent with the location of VLTI K-band dust continuum. The position of the peaks in the hydrogen lines suggests an origin in a compact region with a radius of less than 0.08 AU, 12 times smaller than the forbidden oxygen. This is an agreement of gravity's upper limit on the size of the bracket gamma emission site. This suggests that they are emitted from the dust-free inner disk. Thank you for your attention.
Hello, my name is Sebastian Zarilli and I'm a PhD student at the University of Exeter under Stefan Kraus. I study binary YSOs and their circumstellar environments using near-infrared interferometry. My poster is focused on my efforts to understand the mysteries of the binary Herbig star MWC 166A, a system which has historically had a poorly constrained mass, orbit and even distance. From our observations, and also some historical radial velocities, we found the first ever 3D orbit of the system, which we discovered to be twice as long as previous RV-only estimates. This has allowed us to determine individual dynamical masses and further stellar parameters, as well as to constrain the distance to the system. We also used our observations to study spectral lines for evidence of the circumstellar disk and any ongoing accretion. If you would like to know more, please come and find me and ask me about my poster. Thanks very much.
Hello and welcome to my poster. My name is Samya and I am a research scholar at ICER Tirupati. I firstly thank the organizers for providing me the wonderful opportunity to present my work here. So my research mainly focuses on studying the low mass star formation in extreme feedback driven environments, which can significantly affect the related processes like circumstellar disk evolution, planet formation, IMF, etc. So for this purpose, we perform a multi-wavelength study of Cygnus OB2, which is a highly feedback-driven OB association owing to its massive stellar population. And we start with the deepest and the widest optical observations of this region taken with Subaru Hypersupreme Cam in R2, I2, Z and Y bands, along with archival deep UKITS near IR, Spitzer mid IR, and Chandra X-ray data. We use these data sets to obtain the disk bearing and the diskless population in the region, obtain a median age of the cluster as approximately 5 million years. We also observed that there is a random distribution of the YSOs apart from the central clustering, and we obtain a disk fraction of about 14%, and this low disk fraction can be attributed to the ongoing external photoevaporation in the region. So for more details, please visit my poster. Thank you.
Hi to everybody. I'm Eleonora Fiorellino, a fellow researcher at the Kalkany Observatory in Budapest, and these are the interesting results we found analyzing the Q-tau binary system. Binary systems are perfect environments where to study and test the accretion process, even more if they're eccentric. This is the reason why we computed the mass accretion rate of 8 spectra observed with X-shooter. And as you can see in this figure, we confirmed the pulse accretion model for according to which the mass accretion rate is larger than nearby periastron. And then we managed to discriminate which source of the binary system is accreting the most. So here, for example, you can see that the secondary is accreting the most, while in the previous epoch, it was the primary, which was the main accretor. So in this way, we see that the main accretor changes up to 3 times within only 2 periods. But still, looking at this figure, why different lines traces different main accretors in the same system at the same time? And what does this imply for the physics that regulates the accretion mechanism? If you want the answer, stay tuned for the upcoming paper.
Hi everyone, my name is Bruno Lucidi and I am a final year PhD student at Concoli Observatory in Budapest. My poster is about probing the accretion variability of young stars in the chameleon star-forming region. We combined the high-precision photometric observations of the TESS Space Telescope with ground-based multi-filter photometry and with high-resolution spectroscopy. We included 6 objects in this project, but now I will highlight one of them, which is VWK. And I show the light curves for this object here. This brightening event is a highlight of this set of observations because we managed to get spectra in both the fainter and in the brighter state. But what causes this brightening? The near-infrared color magnitude diagrams show that the source gets redder as it brightens, which is an interesting path. Comparing this path with some models suggests that variable extinction and star spots cannot be responsible for the observed effect. We also looked at accretion tracers in the optical spectra, which show significant evolution. The amplitude change suggests that accretion rate variations might be the major contributor of the observed effect. And indeed, we calculated the accretion rate in each epoch, which showed an increase by a factor of 2.1 by the brighter state. For some additional details on this project, please check out my poster and my upcoming paper.
Hi, I'm Masano Kunitomo at Kurume University. In this poster, I present our recent studies on the stellar thermal and chemical evolution models considering accretion. For the thermal evolution, the entropy of accreting materials is crucially important, as suggested by Hartmann et al. 1997. We revisited this issue with stellar evolution simulations with the modeling of accretion heat. And we found that the evolutionary tracks and isochrons can be significantly different from the standard picture if there's a variety in the accretion processes. In the right panel, we discuss the effect of accretion on the stellar composition. The composition of accreting materials should be highly time-dependent due to the planet formation processes. From stellar evolution simulations, we found that the variable disk composition can alter the stellar composition. So the accretion heat and the variable disk composition should be considered in the realistic stellar models. For more details, please check our poster and feel free to ask questions. Thank you.
Hello everyone, I'm Makoto Unno in my first year of graduate school at Osaka University in Japan. Recent observations suggest that protoplanetary disks encounter molecular cloudlet and receive additional mass and angular momentum during the evolution. Hydrodynamic simulations have been performed to study such cloudlet capture event on 1000 U scale. However, the interaction on disk scale and magnetic effects have not been investigated. So we performed 3D MHD simulations of the interaction between a disk and a magnetized cloudlet on 100 scale, and investigated how magnetic field affects the cloudlet accretion process. This is a result for small and large cloudlet model relative to the disk thickness. Blue color indicates volume rendering of mass density, and lines show magnetic field line. Before the cloudlet collision to the disk, cloudlet tracks magnetic field line, so the cloudlet is braked by magnetic tension force. After the collision, at large cloudlet model, the magnetic field line deforms as magnetic tension force accelerates a part of the cloudlet in the rotational direction. Finally, accelerated region becomes unbound during an orbital timescale. Usually, magnetic field extracts angular momentum of accreting materials such as small cloudlet model. However, we found that the magnetic tension force can accelerate the rotational motion of the cloudlet if the cloudlet is larger than the disk thickness. Thanks for listening.